Hello, welcome everyone. Today we are going to continue on with Unit 5 from the Grade 11 Functions curriculum on sequences and series. Today's topic is all about geometric sequences. So far we've talked about arithmetic sequences and arithmetic series, but we have yet to talk about geometric sequences and geometric series. So just a reminder, arithmetic sequences the core characteristic of them is that every time every term to the next has a common difference. So for example, 2, 4, 6, 8. Well, that's an arithmetic sequence because we always add 2 each time. Or 3, 7, etc., right? 3, 7, 11, 15, etc. That would be another example of an arithmetic series or sequence rather. So a geometric sequence is the same, except instead of a common difference, we have a common ratio. The numbers are separated by multiplying a number called the common ratio r. So I'm going to give you some examples of the geometric sequence. So the geometric sequence, for example, let's say we have 1, 5, 25, 125, 625. This is an example because to get from 1 to 5, we multiply by 5, right? So our common ratio is 5. We multiply 5 again, we get 25. We multiply by 5 again, we get 125. And we multiply that again, we're going to get 625, right? And so on. I'm not sure what we get after that, but we could keep going for this one. So as you can see, really, really quickly, these numbers get really, really, really big. Another common famous one is 2, 4, 8, 16, 32, 64, 128, and so on. This is where we start with 2 and we continue up. There's actually this famous problem. Actually, I guess in the problem they start with 1 and then they do, which works as well, where a child asks for only 1 cent to do his chores every day, and that 1 cent is supposed to be doubled every day, and then the parents think, oh, that's not going to add up very quickly, like, that's not very much money. And they realize that by the time they get to the 30th term, they're paying them a buttload of money that they can't really afford. That is not really going to work for them long term, because maybe the first few days it's working for them, they're only paying 1 cent for chores, then 2 cents, and so on. But even here they're paying $1.28. Eventually they're going to be paying way more than they were hoping to pay for the son to do his chores in those situations, right? So geometric series are very unintuitive when we get to the series part of them, because when we're adding up all these terms, it's going to get to a really, really big number really fast, extremely fast. And each term, especially when we get later and later on in these kinds of sequences, is going to be way larger than the last one, right? So for example, 625 times 5, I'm not sure exactly what that is, but it's 3,125, right? That's a way bigger term. Imagine if we multiply that by 5 again, that's going to be more than 15,000. Multiply that by 5 again, that's going to be more than 75,000. So just a few terms later, we're at numbers completely unrecognizable, just way higher than the terms we started with. And that's something that we didn't really see the same way with the arithmetic series, because everything was equally spaced apart, whereas in this case everything is it's getting larger exponentially, as opposed to just getting larger like linearly, getting larger by the same thing every single time. So let's do an example. Actually, before we do an example, let's talk about the general term. So the nth term, when it comes to a geometric series, is going to come from taking the first term, which we're going to call t of 1, and multiplying that by the ratio to the power of n, right? With n being the number of terms. And we could apply this here. We could say, well, what's the second term of this series here? Well, the first term is 1, the ratio is 5, and we're applying that ratio just once, so it's 1 times 5, which is 5. Let's say we wanted to know the fifth term, which we know is 625, but let's say we wanted to know that. We could plug this in there as well and say, okay, well, the first term is 1, and the ratio is 5, so 5 to the power of 5, or sorry, n minus 1. My apologies. Should have been n minus 1. So r to the power of 4 is going to give us 625, right? 5 to the power of 4 is 625. And the reason it's n minus 1 is for a similar reason as to why we had n minus 1 in the arithmetic series. So I won't go through that again. But if you want to be reminded, please go do check that out for sure. But yeah, that's that. So let's get into some examples here. The first example says, determine the 15th term of the sequence 4, 12, 36, 108, and find the general term for the sequence. Okay, so what is T15? Well, the 15th term is equal to the first term, which is 4, times the ratio, which is 3, right? 4 times 3 is 12, 12 times 3 is 36, 36 times 3 is supposedly 108, and so on. So 4 times r, which is, we established 3 to the power of 15 minus 1, so to the power of 14. So let's see what that is. And my guess, to be honest, is it's going to be a very large number, and we're going to think, wow, that can't be the answer, and it is the right answer, I assure you. So the answer is 19,131,876. And that seems like, whoa, that can't be it. And that's what I mean when I say this kind of stuff is very unintuitive to most people, myself included. It doesn't seem like this sequence with these, fairly small numbers, even 108 being not very big compared to, 19 million. It seems like it wouldn't do that, but just for the sake of it, I'm going to show that it does. So if we plug into our calculator 4 times 3, we're going to get 12. Times 3 again, we get 36. Times 3 again, let's make sure you guys can see that. 36 again. Let's see, that's term 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And as you can see, we got that same thing I said before, 19,131,876, right? And that's because the power of the exponentials, just how fast those exponentials are growing, is what does it, is what gets us those numbers so fast. And let's say we just did term 18, which seems like, oh, that wouldn't be that much bigger than term 15, would it? 18, 15, they're pretty similar. Well, if we just press this equals button 3 more times, 1, 2, 3, oh, well, now we're at 516 million, right? Which, 516 million is quite a much larger number than 19 million. Someone who has $516 million is certainly in a far different tax bracket, far different wealth state than someone with $19 million, even though those are both wealthy people, both quite different levels of wealth, that's for sure. That is for sure. And then we press it another time. Well, that's over $1 billion, right? So the 19th term would be over $1 billion, when over here the 15th term is only 19 million. So it keeps going and doing that even more and more and more as we continue on. So yeah, so that's something I wanted to mention too, is if you get really, really large answers that don't seem right, they probably are. They probably are right. All right, so let's try this one. Now this one we're dividing, so we're actually going to get a very, very small number in this case that's very close to 0, but let's do this one anyway. This one says determine the 10th term of the sequence 256, 64, 16, and 4, and find the general term. Oh, actually, I think I forgot to write the general term for this one. The general term is 4 times 3 to the power of n minus 1. My apologies, I forgot to write the general term. But this would be our general term, which is basically where we fill in what we know, which we know the first term and we know the ratio. But we don't have to fill in n or t of n because we don't know what it is in the general term. They're asking us, in the general sense, what is the nth term based on what we know about this? All right, so let's move on to this one here. It says determine the 10th term, T10, of the sequence 256, 64, 16, 4, and find the general term for the sequence. So let's write out what we know. What do we know? We know that T1, right, our first term is 256. We also know that our ratio is 4, right? 256 divided by 4 is 64. 64 divided by 4 is 16. And 16 divided by 4 is 4. Good. And what we want to know is, well, we know n is 10 because they're asking about t of 10, term 10. So right away, this is going down, right? We keep dividing by 4, and the next term we're going to get is 1, then a fourth, then a 16th, and so on. So this time, actually, I'm expecting a very small number that is very close to 0. Now, it will be a very, very small, it'll still be a positive number, but it'll be a very, very small positive number because we're getting smaller, 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 smaller because we are dividing by 4. Oh, and so sorry, I made a mistake here. I wrote r is 4. R is 1 over 4 because we're not multiplying by 4. We're dividing by 4, which means we're multiplying by 1 over 4. So my apologies for the mistake there. But anyway, let's continue. So here we have term 10, which is going to be n is going to be the first term, which is 256 times n to the 10 minus 1. So that's a fourth to the power of 9 times 256, which is going to be 0.0009766 approximately. So very, very small number, but again, that's kind of what we expected. Now, what about the general term? Well, the general term would be that the nth term in this sequence is 256 times 1/4 to the power of n minus 1. And there we go. All right, let's move on to example 3 and example 4. This one says, find the missing terms for the following geometric sequence and find the recursive formula for the sequence. So I'm going to actually go over what is our recursive formula. So you may remember the recursive formula from the arithmetic sequences video, and this is very similar to that one. Where basically what the recursive sequence is good for is it basically tells us the definition, the main characteristic of our geometric sequence. So that recursive formula states that to find any term of the sequence, all we must do is take the previous term and multiply by r. So this is the general recursive formula for this. Now again, is this formula very useful? Well, not really, because we kind of already know this, right? At the end of the day, we sort of already know that that's the case. And so if we were trying to find, the 20th term and we only had the first 4, to find the 20th term using here, we'd first have to find the 19th term, then the 18th term. Like, we'd have to go through and find all the terms anyway. So the other general formula is a lot more useful than the recursive formula in that sense. All right, so let's figure out how we are going to figure out these missing terms. Well, what we know is that there's 2 missing terms, and to get from 54 to the first term, we must multiply by r, and then to get from the second term to the third term, we must multiply by r, and then to get from the third term to 1458, we must multiply by r again. So we know that 54 times r cubed, right? R multiplied 3 times is equal to 1,458. So using this, we can solve for r, and then we can use this recursive formula in order to figure out every single term. We can figure out the second term by taking the first term and multiplying it by the ratio, and we can do the same thing again and again. And we need to make sure that when we do that, we get 1,458 as term 4. So let's do it. First, I'm going to divide both sides by 54. And that gives us r cubed is equal to 27. And that means r is equal to 3. So our common ratio is 3. So what's 54 times 3? I'm going to actually replace these r's now with 3's. It's 162. 162 times 3 is 480. 86, and 486 times 3 is indeed 1,458, so we have done this correctly. Now, to give the recursive formula for this one specifically, all I'm going to do is take the general recursive formula and put in 3 for r, because in this case it is 3. In this specific case, what we must do to each term to get the next one is we must multiply it by 3. Very good. All right, let's do the same thing for this next one. This one is very similar to our previous ones, but we'll still do it for extra practice. Find the missing terms for the following geometric sequence, and find the recursive formula for the sequence. So again, 7 times some r is going to give us some other number. That number times r again will give us another number. That number times r again will give us another number. And that number times r again will give us 112. So there's not that much difference, exponentially between 7 and 112. So I'm guessing perhaps it's a very small number, right? Like I'm thinking maybe smaller than 2. Let's see. That is just a guess, or maybe around either smaller than 2 or probably around 2, I would say, because it just doesn't seem like there's that much difference. Whereas here there was a huge difference, right? And it was only 3, right? 54 to compared to 1,458. It was, and there were less terms there as well. So I'm guessing this is probably going to end up being, yeah, given that they're both whole numbers, probably 2, but let's see. So 7 times r to the power of 4 is equal to 112. R to the power of 4 is equal to 112 divided by 4, which is 28, and sorry, my apologies. 112 divided by 7 is 16, and then that means that r is equal to 2, right? Because 2 to the power of 4 is 16, or the quarter root of, the fourth root of 16 is equal to 2. So r is 2, so we can use the recursive formula, which is that to find any term, we must take the previous term and multiply by 2 in order to find all the answers. So I'm going to replace these r's with 2's and say, well, 7 times 2 is 14. 14 times 2 is 28. 28 times 2 is 56, and 56 times 2 is 112. So there's our missing numbers, and there's our recursive formula. Well, very good work today, everyone. That is all for today. Next day, we will be talking about geometric series rather than sequences, and learning how to find the sum of the first n terms of a geometric series. And I will see everybody then. Have a good rest of your day, and we'll see you in the next lesson. Bye, everyone.